This video should wrap up my module on Root Locus, and we were doing controller design using Root Locus. And something I should have made more clear earlier on. You know, we were talking about meeting specs. We had a settling time spec, which translated into this vertical line in the complex plane, and a peak overshoot spec, which translated to these slanted lines in the complex plane. And what we're doing here is using the dominant pole concept. By those specs, putting the poles, you know, to meet those specs by putting it in the complex plane this way, that was based on the dominant pole concept. That's why we might not meet specs exactly. Because remember, additional poles and additional zeros affect what actually goes on. So those were based on an ideal prototype second order system, but we don't have that. So we're using it as a guideline. That's why we do MATLAB after we do this sort of analytical work. So with that, I have one more method to show. Actually, we've shown every method. Let me do it with a different controller this time. Last time we did it with an ideal differential controller, which just had the S plus Z. It didn't have an extra pole. That was actually not physically realizable. This time, this example in this video, we're going to use this controller, which is called a lead controller because the pole is going to be to the left of the zero. So here were the two poles of the plant, which is a given. And we're also considering this design point as a given. Here's the two poles of the plant. We're going to add a zero, and we're going to add a pole that's to the left of the zero. Ignore this dashed vertical line. I'm not sure what it's doing there. And here's the design point, -5 plus or minus j 6.8. We're going to want to know where to put the new zero in this pole. Well, the root locus is L is going to be this, right? It started out with just the S plus 1, S plus 3, but we're adding a zero and a pole. So this is the new L. We still got the root locus K. Where to put P? This is something I usually gave my students because you don't calculate it somehow. But one guideline is put it 4 times to the left of the design point. You kind of want it out of the way because we're using the dominant pole concept, so it doesn't affect it too much. You could put it 5 times to the left. We don't put it too far to the left because then we'll be more susceptible to noise, which I'll cover in another module. So in this example, we'll just set P to 20. So now here is our controller, and all we need to do is pick the Z and the K. Here's our L of S. We have all the poles. The rest of this is going to be just as it was in the other Bendit case. We're using the basic complex arithmetic thing that the sum of the angles from the poles from the zeros minus the sum of the angles from the poles has to equal 180 degrees. So when we pick it for the zero, here's our formula. Let me jump ahead for a minute. Here's the key formulas. Put this on a formula sheet so you don't have to pick through it every time. Here's how you know the angle to the zero. We're always going to be working for where's the zero. It's the sum of the angles from all the poles minus some of the angles from all the other zeros, or already, minus 180 degrees. And here's how you calculate the K's. Let's go back to where we were. So we're just using that formula, and we do it to all the poles. The imaginary part, we're doing, what are we doing? We want to calculate 3 different angles. The angle from this pole to the design point, this pole to the design point, and this pole to that design point. We're going to use that formula to do it. So it's the imaginary part of the design point minus the imaginary part of the pole in question, and they're all on the real line, so that's always going to be 0. And then it's minus the imaginary part of the design point minus, excuse me, minus the real part, or it's the real part of the design point minus the real part of the pole in question. The real part of the design point was -5, and we have 3 different poles. They were -1, -3, and -20. So all the minuses become pluses. Do your inverse tangent calculations correctly using your calculator. Add your 180 degrees, and you come up with a number, 71.3 degrees. What is that? That's going to be the angle from this 0 to that design point. 70, what I just said, 70 some degrees, 71.3 degrees. And we had another formula that says, what is Z, now that you know that angle? It's the imaginary part of the design point, which is 6.8. Angle is 71.3, minus the real part of the design point, which is minus a -5, which is 7.3. There's our Z. So our new L is this, and from there we can calculate the K. Flip it upside down. For every S, we plug in the design point. -5 plus J 6.8. So we have a +1, +3, +20. And on the bottom, we'll have a +7.3. You'll combine the real parts and calculate the magnitudes of the complex numbers using Pythagorean theorem, which says do these calculations. Do all that in our calculator, we get a 128. So here is our controller. We're done with the control. The new forward path gain is this. It started out with the S1 and S+3. We added a 0 and we added a pole and the gain to go through this design point. We'll put it in MATLAB and see how we did. We met the settling time spec, which I think was 0.8 seconds. But peak overshoot, I believe, was 10%, and we're at 19%. And that's, like I said, because we're using the dominant pole concept. So we would probably have to iterate here, or maybe we should have changed the design point going into it. But as I said before, the job for my students was to do all this arithmetic, to hit the design point, even if that doesn't get you to meet specs. So this is going to end my Root Locus module. My student's job was hitting the design point. I usually gave them the design point. You got to understand the Root Locus for the type of controller you use. In these examples, I kind of sped through that. You need to know when you added the pole or a 0, what it was going to do to the Root Locus. The rest of it is doing those calculations correctly with your calculator, inverse tangents and stuff like that, magnitudes of complex numbers. And I also usually told my students what controller to use, because there's a little artwork in here, and I wanted to judge my students on the objective part, not the sort of arty, more ambiguous parts. Like I usually tell them where the P was in that lead control. And I only taught actually three types of controller if you include proportional, and only 2 methods: to move the bad pole and bend it. And I have different videos on each of those. And keep a formula sheet Here's the main formulas for when we're doing this. Controller design using Root Locus. And that wraps up my Root Locus module. Next up, we're going to get into the frequency domain.